Günaydın arkadaşlar. Hoş geldiniz. Okay, let's let's start. Uh, we have actually today, yesterday, we have reviewed the black box testing, and yesterday we left off at the beginning of the second example. This is an example for category partitioning method. We were going to show you how, for another example, the category partitioning method can be applied. Well, this is a more comprehensive example for applying the category partitioning method. Well, the first step, as you will remember, of the category partitioning method was to specify the input categories, to specify the problem parameters. And the problem parameters of this of an example, for example, of a specific function like this, the arguments. The arguments we have four arguments, as we yesterday mentioned. We have four arguments for this print file facility. So the arguments look like the number of categories, specification, number of categories, input categories look like they're gonna be four. But in this third argument, you see there are two different uh, inputs that we have to specify. K, which is the font type, and M, which is the mode of printing, which is either normal or bold. So that makes the input categories not 4 as the number of arguments in the facility, but 5, because this third argument contains two different inputs. Okay, well, the next step, the second step of the category partitioning method, as you all remember, is the specification of the equivalence classes for each input category. And as you remember, again, the equivalence classes were the sets of inputs where at each set we have the inputs that we believe as test engineer that the inputs in the set will make the system behave in the same fashion. So let's start with the name of the file. What should be the different equivalence classes for the file name? Well, one would be the name of the existing file given. So this is a valid equivalence class. The name of the existing file will be given. Okay, this is the only valid equivalence class, as a matter of fact, for the file name. What would be a non-valid or invalid file name? One where the file name is not given. So that means we're gonna enter in the command prompt or in the name of the while we call the print file or print uh, uh, facility, we will forget somehow to put the file name in. That will be another test case, all right? No file name given. Another test case that we have to, well, another set of the test cases that we will have to include in the test frame or in the test frame will be a name of a non-existing file given. This is also an NV, a not valid equivalence class. So we will also include those test cases where the name of a file is given that doesn't exist in the directory. And the fourth one, this is another non-valid, not valid or invalid class that will have where the file will have a name that wouldn't follow the syntactic rules. Okay, so we have 4 different equivalence classes for the file name for the first input category. This is the file name. So can you follow how we prepare equivalence classes for each input category? We will do this for the other input categories too. But I would like you to tell me that you understand that for each input category in the category partitioning method, the equivalence classes are prepared, and you understand how this is performed. Do you? Okay, or if you don't understand that, please give me some sign that I can re-explain it. Do you understand that? I would like you to, each of you, to enter your answer here, please. I would like you each to answer me about this. If you don't understand, please say, I don't understand. Otherwise, please give me your answers somehow. Okay, this is also a way for me to understand how many people follow me right now after opening your Zoom meetings. Okay, okay, thank you very much. Looks like only 3 people are following me. That's what I understand from the chat panel. Okay. Uh, for the second input category, which is the number of copies, uh, the first oops, sorry. The first equivalence class is a valid one, which is between 1 and 100 inclusively. So this is what we actually defined when we said that the number of copies will be between 1 and 100. So, and the default will be 1. So this here is a valid class, and it is between 1 and 100, and it is inclusively it is inclusive. And the second one, this is also a valid class. This is for the defaults. When no number of copies are given, then the facility, the code should understand that the default is 1, right? And this is an invalid class, which is less than 1. This is less than 1, n equals 0. And this is greater than 1, which is I'm sorry, this is greater than 100, which is the upper limit of the valid range. Okay. So this is the last equivalence class for the number of copies. For the fonts and mode of printing, we have for the font of printing for K, we have 1 valid class, 2 valid class. Well, this is the valid range of the fonts. This is the default font, which is equal to 1, which should be, which the code is supposed to understand as 1. And this here is the well, this is also a code. I'm sorry, this is also an equivalence class for the fonts. This is an invalid equivalence class. This is the equivalence class for invalid inputs. It is either equals 0, which is the invalid, which is one invalid value for before below the lower limit, and 1 above the upper limit. And these are 8, 9, and 12 belong to the fonts, and 9, 10, and 13, I'm sorry, 10, 11, and 13, these belong to the mode of the printing. Here we have a valid input, m is equal to or m is equal to b, a default one where the m is not given, but the code will understand that the default mode is normal mode. And then there is another one which is an invalid equivalence class for the mode of printing, which is something else than the normal or bold mode. Okay, so that makes altogether 6 equivalence classes, 3 for each input category, font and mode. And finally, we have 3 equivalence classes for the pagination identifier. Well, in one, we will explicitly give the pagination identifier minus NP, And in another one, you will not give the pagination identifier. That means in default mode, it's gonna paginate the input, the file while printing. And here we will give something else than the pagination identifier, and that will be an invalid equivalence class. This also will cover the other syntactically invalid options. Well, now looking at this example, theoretically, how many how many test cases should we prepare so that theoretically sufficient test cases we will be able to use? How many test cases are required at least from the theoretical viewpoint of the black box hypothesis testing? Can you write your answers? Can you write your answers to this question, please? I am. If you don't know the answer, please write "I don't know." But I would like you, if you know, or if you can compute it, please. I want to see your answers on the chat panel. Okay, thank you, Kevsar. And the others who write, I don't know, how did we prepare the number of the test cases in the previous example yesterday? How do we prepare? How do we compute the number of test cases, the minimum number of test cases? Do you remember that? It was okay. How did we do that? And well, if you do, then why don't you answer this question, Minel, for example? We were multiplying the number of equivalence classes at each input category, right? So when we do that, uh, 4 for the file name, 3 for the number of copies, 3 for the fonts, 3 for the printing mode, and 3 for the pagination. So 4 times 3 times a 4, which gives us 81 times 3 to the power of 4 times 4, which is equal to 324 cases. So thank you, Kevsar, for giving me the correct answer. And this is okay. Please remember that in our future examples, you multiply the number of equivalence classes, assuming that in the theory, as in the theoretical black box testing hypothesis, assuming that we are using a single test case for each equivalence class. This is the number of combinations of each set of equivalence class values. So that makes 324 test cases at least theoretically would be enough for testing this piece of code, this facility, print facility. But this might be, of course, too many test cases, 324. So we will, you will see here how we will optimize, how we will reduce the number of test cases. Well, we are gonna introduce an optimizing principle. We're gonna define an optimizing principle, and we're gonna define an extending principle later. Okay, let's see the optimizing principle. What is the optimizing principle? It is it reads that one test case for each invalid equivalence class is fine. One test case for each. So the invalid equivalence classes, each of them should be at least covered in one test case. Okay, what is the second principle of the optimization? Each equivalence class is covered by at least one test case. Okay, so one test case for each, and for each invalid equivalence class is fine. And the second principle is each equivalence class should be covered by at least one test case. So more may be fine, but at least one test case must be for each equivalence class. So well, that each equivalence class should be at one test case. All right, let's look at this. For each one test case for each NV classes, equivalence classes. Well, this, for example, this here covers the first invalid equivalence class. Which one is that? Where there is no file, given. This is it. There is no file name given. This is the first invalid equivalence class for the file name. So we don't see any file names here. All right, the file name is forgotten. This one here is the second invalid equivalence class, xxyy minus c3. Well, this is not a file that can be found in the directory. So here a file name is given, but this file name is not in the directory. All right, and this one here, a file name that doesn't follow the syntactic rules. This is the test case for the third invalid equivalence class for the file name. Okay, so do you follow that, or do you have any questions so far? Do you have any questions so far? Okay. Well, the remaining test cases will have a file name and a correct file name, a valid file name, my file, that can be found in the directory. So this here is for the number of copies. Is this a valid file name or an invalid file name? As you see from the number of the copies, which is 0, this is an invalid file name. So this here is a file name, a test case, I'm sorry, for an invalid number of copies. Okay, so this covers, as a matter of fact, this covers the invalid number of copies, which is the 7th equivalence class. Okay. This one here, is this an invalid or a valid test case? Can someone tell me it is either valid or invalid? Well, my file is in the directory, and the mode here, I'm sorry, the font number here is 100, and which is an invalid font number because the font numbers were between 1 and 9 inclusively. So this is an invalid font number. So this is another test case for the invalid equivalence classes. This is for the invalid font equivalence class, which is I think okay, which is the 12th one. This one here. Okay, this is an invalid test case for the mode, because modes can the mode of the printing can only be N or B, or it may be missing. Then the default is normal, but this is an H, which is an invalid entry for the mode of printing. So this is for, I think, for 13th equivalence class. Yes, this is for the 13th equivalence class. And this one here, this here is for the last equivalence class, I guess, for this one, for the 16th one, something else than non-pagination is given. So this here is supposed to be NP, but it is HJK, so this is an invalid entry for the pagination identifier. Okay, so this is another test case for the 16th equivalence class. Can you follow? Do you have any questions? Do you understand what's going on? Okay. Well, let's now we have 7 test cases here, 7 test cases and 16 equivalence classes. All right. So let's look at a matrix that relates the equivalence classes with the test cases. Well, for the first one, for example, I'm sorry, for the first test case, we look and we see that we have an invalid class covered in this first case, and 1, 2, 3, 4 valid classes are covered. Pluses denote the valid classes, and minuses denote the invalid classes. Okay, and the class indices are also shown here. For example, this first test case covers the second, the fifth, the ninth, the 11th, and the 14th equivalence classes. Let's look at it as an example if it really does. This, for example, we said that it covers the second invalid equivalence class. This is an invalid equivalence class. No file name given. Actually, no file name is given here. It also covers the number of copies, and this is a positive. This is a valid number of copies. So let's look at the valid copies. It is number 5. So let's look at the matrix. Okay, number 5 is also covered. All right. It is further. It covers NP, the pagination, and this is a valid pagination. Oops, sorry. This is a valid pagination. Let's see. The 14th NP is given, so it should cover the 14th equivalence class. Let's go look. Okay, 14 is also covered. What does it cover further? Well, the number of copies are covered. Okay, pagination is covered. There is nothing else here. But so this, the font number and the print mode, they are also covered, and their defaults are actually covered. So let's look at the defaults for M11 and default for K9. So 9 and 11 we should see in the matrix too. Well, 9 and 11 are also here. So we have these four, also these four valid classes and this invalid class covered in the first example. Okay, so the second example covers 3. The second example covers the 3, this is an invalid class, 5, 9, 11, and 15 this time, etc., etc. So I'm not going to go into each of these, but I will have you pay attention to the to the to the examples. Each of these test cases covers one invalid equivalence class, as you see. This one, the second, this one, the second test case, the third invalid class, the third test case, the fourth invalid class, the fourth test case, the seventh invalid class, the fifth one, the 12th, the sixth one, the 13th, and the seventh one, the 16th invalid classes. They cover the relevant invalid classes, equivalence classes. So, well, altogether, now we have 7 classes, and looking at these examples, we see that 14, 16, 15, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Each of these equivalence valence classes are also covered at least in one test case. All right. So okay, looking at, for example, 1, we see that 1 is covered in 4 test cases, as a matter of fact. So that from this table we can understand that optimizing principle, both principles of the optimization is fulfilled, as a matter of fact. All right. But there are only 7 test cases. 7 test cases which fulfill the optimizing principle may not be enough for such a piece of code, which is with 4 arguments and 5 input categories. So let's look what we further do. We have an extending principle to extend the number of test cases so that a more comprehensive, a more quality black box testing can be applied to the example. And what do the principles of extending say? Combinations over the number of parameters should be also tested. Well, what combinations? What are these combinations? Name of existing file always given. Okay, so we give the name of the existing file in all test cases. That's one principle. The second one is a test case where all parameters are missing. So no parameters should be there, so that all defaults should be given at one test case at least. A test case for each individual parameter where 1 should be present. A test for each parameter included in the set of pairs and each parameter included in the set of triplets, and all parameters should be given. So 4 of them should be present. So these test cases, a test case covering each of these principles should also be added to the test frame. Now let's look at the further test cases that fulfill these extending principles. Now at the eighth one, my file is given, but no other identifiers are given. Well, this was the first principle, name of all, I'm sorry, the second principle, name of, well, here name of existing file always given at the test cases, and this one is also fulfilled at the eighth test case here. No identifiers are given, no parameters are given. In this one, the number of copies is given. This one for number of copies. Here, this one, the font is given only. Here, the mode is given only as bold. And here, the number of the pagination identifier is given only. So, one present principle, only one present, the principle of test cases where only one input category is given are fulfilled here. Okay, and here the combinations of two are covered. The font and mode, okay, here font and mode are covered. Here number of copies and pagination are covered. So this too fulfills the third, I guess, the third I'm sorry, this fourth principle, each parameter included in the set of pairs. So we have each parameter included in the set of pairs in these two, and now I'm sorry, in these two. Now we will cover triplets. This here covers copies, font, and pagination. This here covers copies, printing mode as bold, and pagination. And this here covers all of them. Okay, so here the triplets are covered. Here here all parameters are given, and this is the final test case that fulfills both optimizing principle and extending principle. So let's look at the big matrix that includes all test cases plus all principles, all 16 principles. I'm sorry, all 16 equivalence classes. As you see, well, the extending principles are, of course, extending principles are composed of test cases where the valid equivalence classes are covered. So that's why you don't see the invalid equivalence classes, because the invalid equivalence classes were covered in the first 7 input cases. This one shows the test cases that are added in the second salvo, in the second for the extending principles. I'm sorry. These are the test cases that are added for the extending principles. So here no invalid classes are covered, because extending principles were only for the valid classes. Okay, so here you see that each valid class is covered in this case. Do you have any questions for this example about the black box testing? Do you understand how we prepare the category partitioning method for the for a more complex example, for this example, for the printing example. Do you understand that? Do you have an idea? Do you have an idea how we will form the category partitioning uh, testing? How will we will apply the category partitioning method to some example, to some software testing problem? Do you have the big picture in your minds? If you have any questions, please raise your hands or let me know. Give me a sign from the chat panel so that I can answer your questions. This is extremely important. The category partitioning method for black box testing is extremely important that you understand that. If you don't understand any portion of it, please ask your questions. Well, this is the end of the black box testing uh, chapter. Again, black box testing is a functionality testing approach. It tests the software product from a functionality viewpoint. It doesn't require the source code, but of course, having the source code, well, we will have the source code to test it, but black box testing is a testing approach where the software, where the source code is not required, is not actually necessary, because this is a functional testing that tests the functionality using the specification and requirements document of the software product. It is based upon the specification of the software product. Okay, so and the details are given to you for the category partitioning method in two examples explicitly and in details. So if you have any questions, please do raise them. Otherwise, I will finish this chapter today. Okay, then let me, before finalizing this discussion, let me ask you several questions from the category, several simple questions from the category part, from this chapter actually. And please, all of you people, give me answers, write your answers to me for these questions. The first question is, what is the name of the testing method that you have learned in the black box testing approach? What is the name of the method? I expect an answer from each of you people who follows this lecture right now. The name of the method that follows the black box testing approach. Okay, I am expecting answers from all of you people who is now listening to the lecture. Well, this is actually a question from yesterday. We have talked about this yesterday too. We have reviewed this yesterday, and we have actually talked about this last week too. But I thank you all for your answers. I'm getting only 5 answers, not more. So this is for for me feeling sorry, really. Well, thank you very much, Kevser. By the way, the correct answer is category partitioning. Okay, another question. Another question. Uh, how many steps do we have in category partitioning method? Again, I expect an answer from all of you people who is following the lecture right now, who are following the lecture right now. Okay. The correct answer was 6. Yes, 6. Okay. Another question is, how many out of these 6 steps are performed automatically using a testing tool? Okay, the correct answer is 3. The last 3 steps are the steps that are applied automatically, that are performed automatically using a testing tool. Okay, and one final question: what are the names of the set of principles that are applied to the in the category partitioning method? The name of the principles, set of principles that are applied in the category partitioning method. The 2 sets of principles that are applied in the category partitioning method. Okay, the correct answer is optimizing principle and extending principle. All right, I will take a 10-minute break and then see you at 9:30. Bere bir soru sormuşsun galiba. Şimdi gördüm. Pagination, örnekteki pagination için iki tane valid option var. Bir tanesi NP, bir tanesi de yani bir tanesi minus NP giriyorsun, bir tanesinde de girmiyorsun default olarak. İkisi de valid bunların. Rica ederim. Okay, let's today we will start with the white box testing approach. After the black box testing approach, which is a functionality testing paradigm, we will look at the white box testing now in detail, which is a structural, which is more a structural testing approach where the source code is required. This testing approach works on the source code to test the software product. All right, let's start with the discussion. This is a piece of code that we will show the in which we will show the motivation for the white box testing approach. Why is white box testing important, and what does it cover that the black box testing uh, cannot cover, let's say. Okay, this is first of all, please note the small size, note the compact size of the piece of code. Okay, this is a very small code, but this is very suitable for white box testing approach. So let me first remind you that the white box testing is applied mostly to uh, code with a rather compact size, with a rather small size, because if the size of the code is larger, or while the size of the code grows larger, the testing, the white box testing, the structural testing becomes more and more, or approaches more and more to being infeasible. Okay, because of the number of possible execution paths that we have to cover using the test cases in the white box testing. All right, so let's check out this piece of code. Here we read a number. Here, if the number is not between 0 and 100, then we assert an error message. Otherwise, what we do is we initialize sum and x And while the number is less than I, okay, we add the number, we add up the numbers, and we increment x. So that is actually at the end what print what's what this program prints is the summation of the numbers up until the value I. Okay, here there is only one thing that is added to the that is different than summing up all numbers up until I is if I is equal to 10, sum is initialized back to 1. Otherwise, sum gets sum gets or holds the result of the summation. So this here is something that that makes the whole thing a little interesting. All right, if I becomes 10, then sum is initialized. So for all values starting from 10 or greater, the values are initialized. The sum value is initialized to 1, and it starts back from as if the summation results in values starting from 0 or so. So, for example, for the value 10, the summation is equal to 1. The result of the sum is equal to 1. If it is 11, then it is equal to 1 plus 1, 2, so etc. So this is it doesn't perform as we expected from a summation formula. Okay, now let's look at the next slide where we will show you the black box test cases for this piece of code. For example, I equal 1, I equal minus 1, I equal 0, I equal 1, I equal 50, 99, 100, and 101. These are all, the black box test cases are all okay. Okay, so if it is equal to 10, then it is initialized to 1. Otherwise, it is not the value of sum is not changed. So for all these values, there is no problem in the black box test case. Okay, and the black box test cases, as you see, we have a valid range between 0 and 100. So we will try. We should try in the black box test. What are the black box? Okay, let's ask you this question. This is for this piece of code. What kind of, if you don't see this code, what typical black box test cases would you prepare? What are the typical black box test cases for this problem if you don't see the code, but if you are informed that it should perform, or it should compute the sum for all numbers or all integer numbers between 0 and 100. What are the test cases that you would prepare if you don't see this code here? Okay, yeah, what would be the test cases? I'm expecting an answer from you guys or people. What are the test cases? Okay. Uh, well, we will prepare some boundary test cases, right? And some typical test cases, right? A typical test case would be the number right in the middle of the range, right, which is 50. And the boundary test cases would be -1, 0, 1, 199, and 101, right? These would be the typical black box test cases, right? Let's look at them again. -1, 0, 1, 50, 99, 100, and 101. But 10 is not a typical black box test case, right? Because it is not in the middle. I mean, without seeing this piece of code, we would actually not select 10 as a typical valid test case. Don't you think so? 10 is not a typical test case for testing or for being a representative for the valid numbers. So, uh, so this is what may lead us to a failure unless we see the code. Because the code here, when we see the code right away, as Nur Deniz tells us, that 10 should be a good test case for us to check out, right? because there is this I equal to 10 in the code, but we don't see that. And the functionality of this piece of code is to sum up the values up until an integer I. All right. So that is what we're missing. That is what is missing in the black box testing. Since we don't see the code, if we see the code here, we right away understand that I is equal to 10 is a good test case. All right, I is equal to 10 is a good test case because it is in the code. But the functionality of this code, without seeing the code, functionality of it tells us that boundary cases should be tested, and the typical valid value should be tested, which is the one in the middle mostly. Do you understand? Do you understand what is going on? Do you understand what difference white box testing makes when we see the code? Do you understand that? Okay, perfect. Well, we don't have this. We don't have I equal to 10 within the black box, typical black box test cases. But it is a key to seeing some bug in the code. All right. So let's go back to white box testing principles. Here the details of the source code are analyzed, and the design of test cases are based upon the code structure, not the functionality, but upon the code structure. The execution path, what does it mean? How is it defined? It is a certain sequence of program statements executed when starting a program with a certain input or certain test case. Okay, different test cases create different execution paths, or different test cases run through different execution paths. All right. What is control flow testing? What is control flow testing? It is based upon the execution order of the statements. Control flow testing is a testing way that is based upon the execution order of the statements. And what is data flow testing? It is a testing approach which is based upon the processing of the data during the execution. So we will use these terms interchangeably whenever we feel is necessary. All right. So please learn them, learn and understand them. Okay, we will use, while discussing the white box testing approach, we will use the control flow graphs and data flow graphs. What is a control flow graph? It is an abstraction of the program's control flow in graphical form. And data flow graph is an abstraction of the program's data flow for a certain input variable in graphical form. Usually, it is an extension of the control flow graph. Well, if you remember from your first class, from your freshman years, the data flow diagrams, control flow diagrams, we will make use of these diagrams in white box testing approach. And how will we exploit these graphs? We will actually design test cases from these graphs. Well, there is a concept called coverage. Let's see what it means. Coverage is the relative amount of statements and others. It should not only be statements, it may be also a path coverage or a statement coverage, etc. It is the relative amount of statements or paths executed during testing computed from control flow, data flow graphs. So as I said, the control flow and data flow graphs will be extensively used in the discussion of white box testing. So that's why we are going to define these flow graph structures. Well, this, for example, is a sequence of statements. All right, this flow graph structure tells us that a sequence of statements are running. We can also show it like that in a more compact way. This here is a decision structure. All right, this here is a point of decision in a flow graph. The input comes here. Actually, this is the input, or the flow. The flow is at this point, and at this point, if the condition is true, the flow of control goes to S1. If the condition is not true, the flow of control goes to S2. And in this case, S2 is executed. And whichever way is selected, at the end, the flow of control comes at this point, or arrives at this point, rather. Okay. This is a typical decision structure, or we can say that it is a conditional, it is an if statement, it is a conditional statement. This may also be true for an entry to a loop, or this is a decision structure in general. If, for example, condition S, then S1, else S2. This is the corresponding code for this control flow structure. Do you know these? Are you familiar with these? You should be, right? Okay. All right. Well, let's continue with the flow graph structures. This is, for example, a flow graph structure for the while do loop. while condition, okay, while condition do this here, okay, this here is a while do loop. So if the condition is true and the set of statements S is executed, and then the execution comes back, or the control flow comes back to the condition. And if the condition is true, only if the condition is true, then the execution of S continues. Otherwise, uh, uh, otherwise the execution is exits the loop and continues. All right. So in this case, okay, in this control flow structure, S may be executed 0 or more times. All right. If the condition is not true at the first try, then this sequence of statements is not executed, and the control flows through this path. Okay, this here is a do while statement as opposed to while do. This in this uh, execution, in this structure, this sequence of statements is executed at least once, then the condition is checked. If the condition is not true, then this is not executed a second time, but it is executed regardless of the condition at least once, right? If the condition is true, then the execution for a second or more times continues. In this one, we have a for loop. If, okay, S1 is an initial statement, it is always executed. Then, if the condition is true, then the statement S is executed. And then S2 is executed after S. And then the condition is checked whether or not it is true. If it is not true, then the execution exits the loop. Otherwise, the execution of the loop continues. Well, this one here is a switch case statement. At this point here, whether the enumeration, enumeration, I'm sorry, the enumeration is checked to see, checked out to see whether it is correct or not. If it is, I'm sorry, it's not checked whether or not it is true, but it is checked out to see which value it has. If it has the value of enumeration 1, then S1 is executed. If it is equal to enumeration 2 value, then S2 is executed, and etc. And if it is equal to enumeration n, then Sn is executed, and afterwards the control flows through this path. So these are the various flow graph structures that we use to constitute, to form the control flow graphs of a typical C code. Okay. All right. Let's look at the control flow testing now. Let's see what coverage is in some more details. Let's discuss the coverage concept. Well, coverage tells us how extensively the program has been or will be tested with a given set of test cases. All right. So coverage is the concept of coverage is extremely important in white box testing, because it shows us, it tells us, it gives us the hints of how comprehensively, how extensively we will cover the code in our set of test cases. All right. Well, please, before the second remark, imagine that you're using a control flow graph composed of such structures. Okay. These are nodes, decision structures, edges, uh, of the control flow graph. Again, this is a node, this is a decision node, this or this, these are the edges of a control flow graph. All right. Now let's go back to this. Here, the relative number of nodes, that is statements, in the flow graph executed during testing. Okay? The relative number of nodes or statements in the flow graph executed during testing. For example, the statement coverage tells us the relative number of nodes or statements in the flow graph executed during testing. The branch coverage, for example, another version of coverage, it shows us, or it provides us with the relative number of edges, control transitions, in the flow graph traversed during testing. All right. So, well, let's look at the statement coverage. Each node, okay, what is the statement, the principle of statement coverage? Each node or each statement has to be executed at least once. Okay, and the percentage of the statement coverage shows us how many nodes or how many statements during a testing in the flow graph is executed. Branch coverage, principle of branch coverage is that each edge or each transition has to be traversed at least once. So if you wanna attain, if you wanna reach 100% branch coverage, then you have to test each transition, or you have to traverse each transition at least once in your test cases. Do you understand that? For 100% statement coverage, you have to test each node or each statement at least once. For 100% branch coverage, you have to traverse, during your testing, you have to traverse each test or each transition at least once. Do you understand that? These are the principles for statement coverage and branch coverage. Okay, let's look at the next remark. A large number of variations of different coverage power. A large number of variations of different coverage power. Well, these statement coverage and branch coverage, and we also have other versions of coverages. You will see that these provide us with a large number of variations of different coverage power. Well, there is a special target that is loop testing. We will see that in a bit. But what is an execution path? Let's look at it in some more detail. It is a sequence of nodes and connecting edges from the unique begin node of the flow graph to the unique end node of the graph. It is a certain instance of the relevant program execution. One path means one instance of program execution from starting from the begin node up until the unique end node of the graph. It may contain the same node several times because of the loops that exist within the execution path. Okay, now we will see here several things. Well, look at the for example, this path here. This is an execution path. Do you follow the mouse, when I do this, do you follow it? Everyone can see it? Okay. Well, let me draw a line here. This, for example, this is an example execution path. All right. And this here is another execution path. Using these two execution paths, what do you think is the statement coverage? What is the value of the statement? How many statements did I cover? Gözükmeyen nedir? Okay, this is one execution path, all right? And this is another execution path. Okay, so these are the two execution paths. And if I test these two execution paths through these two execution paths, what is my statement coverage? Well, no. Well, okay. Let me tell you this. I tested this path, this execution path, all right, and I tested this execution path, all right. I run using my two test cases through this and this execution paths. What is the percent of the statement coverage? Yes, all nodes are tested once, at least once. So that means I have 100% exactly. I have 100% statement coverage because I tested each node at least once. Well, this one I tested twice. This node I tested twice, and this node twice. So that means I tested all nodes at least once. That means I have 100% statement coverage. Do you all understand that? Do you have any questions on this statement coverage? Do you want me to explain it once more, or should I continue? Well, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 nodes here. At the first, okay, in this first execution path, the 7 nodes are executed. All right, these nodes on this execution path, and at this green path, oops, sorry. At this green path, the remaining nodes, the 1, 2, 3, 4, 5, 6, 7, these 7 nodes are executed, and all nodes this way are executed using these two test cases through these execution paths. Okay, so the statement coverage is perfect using these two test cases. All right. Now, let me ask you another question. What is the branch coverage of using these two test cases through these execution paths? What is the branch coverage? Okay, can you be more specific? How do you compute these percentage values, 50% or 66%? Let me clear that again. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, okay, 12, 13, 14 branches, 14 branches, all right? So how many branches did we cover using these two test cases? We only didn't cover that one, all right? Out of 14 test cases, we only didn't cover that one. So 1 out of 14 is not covered. So 13 out of 14 is covered, okay? So times 100 times 100, this is the percentage of the branch coverage using the two test cases through these two execution paths. Do you all understand that? No, no, Frat, this is not path coverage. This is not path coverage. This is branch coverage. We have 14 branches in total. We only don't cover this one, so we cover 13 branches. So the percentage, oops, I am sorry about this. The percentage is this: 13 over 14 times 100 is the percent value for the branch coverage using these two test cases. Okay? Everyone understands that? Anybody who has a question on this? All right. If you have a question, please ask, because these are important subjects to you should understand these. Okay. Now, in this first control flow graph, we didn't have a loop. Now, in this second one, the one in below, we have a loop also included. Okay. Well, now let's see. We have this one. Okay. We have this one. And we have this one. So let's, okay, to cover everything. Well, let's ask this question. With this execution path, what is my statement coverage? What is my statement coverage? Can you all give me an answer? Only this one test case, and it tests through this execution path. What is my branch coverage? What is my statement coverage? Exactly. Exactly. 11 is not a, where did you find 11? 11 is not a correct answer. I'm asking for a percent value. Yes, 7 over 13 or 7 over 13 times 100 is the best answer. But 7 nodes out of a total of 13 nodes are executed or are tested through this path. All right. So 7 out of 13 times 100 is the correct statement coverage percentage. Exactly. All right. Now, what is the, for the same execution, for the test of the same execution path, what is the branch coverage now? Well, I have two correct answers. I have two correct answers, 50%. Do you have a problem understanding how it is computed, or you just can't count the number of count the branches, or what? It is exactly, we have 8 branches here, and we have 16 branches in total, so it is 50%. With that execution path, we have 50% branch coverage. All right. For a second one, okay, this is the first execution path, and this here is the, well, let me draw this. I'm sorry. Let me draw this using another color. Okay. And this is the second execution path. Okay, with these two, with the test of these two execution paths, now what is the statement coverage? What is the statement coverage? Exactly. Exactly. We have, yes, we have not covered these three nodes. So 10 out of the 13 nodes are covered. So the correct answer is 10 over 13 times 100. Exactly. All right. Great. What is the branch coverage for the same tests of these two execution paths? Out of 16, we have not covered 1, 2, 3, 4. So 12 out of 16 are covered. So that makes 75%. Exactly. Exactly. Great. So, well, all those that have answered seem to understand it correctly. Okay. Do the others have a question about the statement or branch coverage? Okay. Well, let's continue then. Uh, well, this here is the tells us, this slide here mentions the statement coverage criteria. And this here is a please pay attention when you read this. This here is a formal expression of the statement coverage criterion. A set P of execution paths. So P is a set of execution paths. It satisfies the set of P, a set P of execution paths satisfies the statement coverage criterion if and only if for all nodes n in the flow graph, there is at least one path P in P such that P contains the node n. Each statement of the program is executed at least once during testing by some test case. Each statement of the program is executed at least once by some test case. That makes the criterion met complete, or 100% statement coverage. Criterion not met, partial statement coverage. This is strictly less than 100%. Well, here we will exclude begin node, end node, and junctions. Okay, complete coverage surprisingly hard to achieve in practice. And here, that code, that code we say, the code that is never reached, or the conditional compilation are two concepts to discuss. So now, given this statement coverage criterion, again, a set P of execution paths satisfies the statement coverage criterion if and only if for all nodes n in the flow graph, there is at least one path P in the set of execution paths P, such that P contains the node n. That is equivalent to saying that each statement of the program is executed at least once during testing by some test case. If this is true, okay, then we say that the criterion, statement coverage criterion, is met, and we have a complete statement coverage, that is 100% statement coverage. Okay, so let's go back to the examples of the previous slide. Now, for a complete statement coverage at this above control flow graph, how many execution paths do we need to test? My question is, again, to attain a complete statement coverage criterion, at least how many execution paths do I need to test using one test case? Okay, Abdullah has a correct answer. Kevser has a correct answer. Fırat has a correct answer. No, not 5. 2. 2. 2. And these are this one, okay, this one, and this one. These are the two execution paths that I need to test with at least one test case, so that I can come up with complete statement coverage in this control flow graph. How about this one? How about this one? How many test cases? I'm sorry, how many execution paths do I need to test with at least one test case, so that I attain a complete statement coverage criteria, complete statement coverage? For this one, okay, 2 are not enough. 2 are not enough. It should be 3. This is the first one. Okay. This is the second one. And this is the third one. So 3 must be enough. If I using one test case for each of these execution paths, why 2? Why 2? Why 2? No, this, okay. Well, well, that's a good point. That's right, Abdullah, or Frat, or Metehan. This is, well, this actually covers all nodes. This, yes, this covers all nodes. Well, well, okay, that's a good point. You say, you guys, those are not really, no. When you said 2 execution paths are enough, that is also a correct answer. Well, in if we select the execution of at least the execution at least one once, okay, if we select the execution of the loop at least once, then that covers also these nodes. So if you said 2 execution paths, this is also not incorrect. This is also true, but we have to the common understanding of software testing is for a single for this path where the loop is not executed even once, should also be separately tested. Okay, but if you say from the theoretical viewpoint, if we test it at least once, then we cover all nodes here and here. So 2 execution paths are sufficient. That is not an incorrect answer. That is a correct answer too. Okay, that's right. So Fırat, Metehan, Abdullah, you guys also answered correctly. 2 execution paths are theoretically enough, but another test case that would test additionally this execution path is not a bad idea. Do you understand me? Okay. All right. So if you like, let's stop here and let's continue white box testing in the next week. All right. So thank you all for joining the class, and see you next week.